Hello guys, this is Dave. Today we will discuss the basic concept of center of mass and its calculation for a few objects. Okay. So what is center of mass? Generally known as COM. Okay. You see, center of mass for any body, for example, if this is a body, is a point where its whole mass or weight is concentrated. Okay. For example, let's say if O is a point, then if the center of mass lies at O, then the whole mass or weight of body is concentrated at O. Okay. Yes, mass is obviously distributed at other points, but if you hold the body by this point, if you apply a force on this point O, then the whole body will be stable, it will not topple. Since the whole weight of the body is concentrated at O and the whole mass is at O, so the whole weight of the body will be applied at O, and we can just write the equation of weight of the body by this. This is the FBD of body, free body diagram. You see, I have just depicted the body by O because the only force at O is mg, because the whole weight is concentrated here due to the whole mass being concentrated here. Okay, that is known as center of mass, where the body will not topple. Okay, but first we need to first understand what is torque. Torque is an action of force which causes rotation. This is a basic definition of torque. Okay, you see, torque is a vector and it is in the formula terms known as R cross F. This is torque. Have you ever seen a door? You see, for example, this is a door. We always see the door being hinged to a wall. This is a wall and this is a door, and this is the knob of the door. This is the hinge point. Okay, so if we apply the force at the hinge point, the door does not move. Okay, no movement. But if we apply the force here perpendicularly, then the door will move. Then the door will open and the door will subsequently close. Okay, this is because force is being applied at some distance. Here there is no distance from the hinge. Okay, so the axis from where the body is supposed to rotate has some distance. It has to have some distance. You see, this is R. So due to this being R, there is a torque being produced. And since R cross F is there, this is a basic formula of torque, R cross F. So R F sine theta. So you see, sine theta is the angle between R and F. Okay. So since this is the angle, here the angle is 90, so torque will be equal to Rf. This is the magnitude of torque, and the body moves. So torque causes rotation. Okay, in general, torque causes rotation. Now why is this useful? This is useful because, for example, in a seesaw, here there is a balancing point, here there is one person, here there is the other person. Okay, and you see, if for example they have different weights, m1 and m2, and these are different distances, r1 and this is r2. Okay, but still the seesaw is balanced. Okay, despite, for example, say m2 is greater than m1, even if this happens, then also seesaw is balanced. This is because the seesaw is not just depending on the balance point. You see, is the seesaw, the toppling of seesaw is not only dependent on the mass or weight, it is dependent on the torque. Okay, hence even mass, if masses are unequal, but the torque must be equal. This means the force here on the person would be m1g, right? Sorry, m2g. And m2g, since it is being applied at a distance r2 from P, hence it will cause a rotation of P. Okay, so P will rotate. Since rotation occurs at the point of hinge only, since this is a straight rod, this cannot move by itself, it has to rotate because it is very straight and rigid. This is a rigid rod. Okay, so P will rotate due to the weight m2g being producing a torque. So see, tau 2 equal to m2g, and r cross, since it is vertical and since it has 90 degrees with r2, so it will be r2 m2g. Okay, so this should have moved here, but in addition to this, there is a torque over here also. m1g is also producing a torque in the opposite direction. If this is clockwise, this is anti-clockwise. So m1g r1 is the torque being produced by m1, and m2g r2 is the torque being produced by m2. Since P is balanced, both torque must be equal. So m1g r1 equal to m2g r2. Gg gets cancelled out. Okay. So m1 r1 equal to m2 r2. Okay. This is the condition of balanced torque. This is the moment of masses also. You can also say this is the moment of mass. Okay. It doesn't matter because moment of force is r cross f. Moment of force is called r cross f. Force times distance. Okay. This can also be called as moment of mass. Okay. So this is the basic principle of torque. It helps to rotate. So now we go back to the original question. You see, this was the object. Alright. And I had assumed this point O as the center of mass. Alright. Here the whole mass is supposed to be concentrated. Now for this to happen, the whole torque of the body, you see, for example, these are small masses m1, m2, m3. The torque produced by the weights of these small masses about any point must match the torque produced by the whole weight concentrated at O. Then only the center of mass is supposed to lie at O. What do I mean by this? For example, if we take just this body and we take this axis, alright. For example, this is the axis. Now O has a distance for say r. Okay, O has a distance. O is at distance r from axis. Alright. This is y axis, and whatever it is, it does not matter now. Say m1 is at a distance r1, m2 is at a distance, so this is m3, so this is r3, and m2 is r2. Okay, so now the whole torque produced by these small masses must match the torque produced by the point O where the whole mass is concentrated. Okay, this is because if the whole mass is concentrated at O, the torque produced by it at this axis, at y axis, will balance the whole torque. That is the main crux of center of mass. So we suppose whole weight concentrated at O. Alright. And the individual masses. So torque net about y is torque net would be equal to m1g r1 plus m2g r2 yes plus m3g r3 dot mig ri, right? This is the net torque about y. Okay, this we know. So torque net was this was m1g r1 plus dot mig ri. This net torque, now this was the object and these are the net torque by the masses, and this is O. So let us concentrate this as mg. M is the whole mass. Okay, and this is r. So this torque net must be mgr. Alright. So this is m1g r1 plus m2g r2 dot mig ri, and gg gets cancelled out, and r becomes m1 r1 plus m2 r2 plus dot mi ri divided by m was the whole mass, so m1 plus m2 plus dot mi. Alright, this is the center of mass. Alright, this r is the center of mass. We call it RCOM. Okay, so This is the definition of center of mass, where all the torques balance out each other, alright. And where the whole mass, the torque due to whole mass is balanced by the torque due to individual masses, alright. We can also write this as RCOM equal to summation MI RI divided by summation MI. I would go from 1 to n. This is the standard definition of center of mass for any object, okay. Now you see this standard definition, RCOM equal to summation I equal to 1 to n MI divided by summation I equal to 1 to n MI. This is for a discrete body, okay. But in general, in reality, we know no body is discrete, okay. As far as I know, real-time masses are continuous, alright. So if real-time masses are continuous, we cannot take this expression. So we have to take it in the terms of calculus. So RCOM here becomes now integration, alright, integration x, okay, integration x, yeah, dm divided by integration dm. This is the standard definition of center of mass. X is any point from the axis, okay. This is a standard definition of center of mass. Integration x dm divided by integration of dm. Because mass is continuous. Since mass is continuous, we can take infinitesimal mass dm, and this can be integrated over the point from which the center of mass is to be calculated. Alright, so this is the standard definition now. So now we solve a problem, okay. What is the center of mass of rod of length L and mass m? What is the center of mass? I want to find out the center of mass. Typically speaking, rod of length L obviously is symmetric. Everyone knows it is center. But knowing and solving are two different things. You have to derive. Alright. Now, always remember, first take an axis. First take axis from which center of mass will be calculated, okay. You cannot calculate center of mass in the air, you have to take an axis, okay. Suppose this axis I take, this is an axis y, alright. Now I want to calculate the where will be the center of mass from this axis. So I take an element mass. Since this rod is continuous, I am taking an element mass. Alright, say this element mass is dm. Okay, this element mass has a width dx at a distance x from the axis y. Alright. So this is the situation now. Now I want to find out what will be dm. What will be dm? Since I am taking mass in terms of length, alright, so dm can be equal to lambda into dx. Lambda would be the mass per unit length, as mass is continuous. Since mass is continuous, I can take m by l as lambda, which is constant. So for any distance x, this will be done when, for any width dx, the mass per unit length, since it is constant, the element mass for a length element dx will be lambda dx, okay. So dm equal to m divided by l into dx. This is the element mass. Now I want to find out the center of mass. What will be the center of mass? Center of mass would be r equal to integral x dm. What is x? X is the distance from the axis from where we want to calculate the center of mass. I want to calculate the center of mass from this axis y. So I want to know how much distance the center of mass is from this axis. Alright. Divided by integration of dm. So I now know x and dm was m divided by l into dx, and integration of dm would be m obviously. Mm is constant, this goes out, and x will go from 0 to l. Why? Because we are calculating from y. We are calculating from axis y. So x will go from 0 to l. Alright. So integral 0 to l, this 1 by l comes out, x dx. and x dx is x square by 2, and r would be equal to, putting limits we get L square by 2, L gets cancelled, so it is L by 2. So you see the center of mass is at distance L by 2 from this axis. Alright, L by 2 from this axis. Why? So you know what is L by 2 from this axis? This is the midpoint. Hence we get the center of mass as midpoint of the rod. Alright. You have to solve these things, and this is the general proof of these things. Okay. This is the general proof of the center of mass. Alright. Now let us Now let us twist this problem. Okay. I take a rod. Alright. Now I want to find out the center of mass from this axis, from the axis passing through midpoint. Alright. Now we take the axis passing through midpoint as y. Now I want to find out the center of mass from this axis. Now what do? Now you see, first of all, I take an element mass, say dm. The standard, I am following the same standards as I did before. This dm has a weight dx. Okay. This is at a distance x. So what will be the center of mass? You see, this was integral x dm divided by integral dm, right? And what was dm? Dm was m over L dot dx. M over L is constant, as mass is continuous. I am taking this as lambda, mass per unit length. Alright. When something is continuous along anything, you can take the quantity divided by that thing. For example, if mass is continuous along length, you can take the mass per unit length as constant. Okay. So r would be equal to integral x times m divided by L dx, and integral of dm would be m. This gets cancelled out. R would be equal to 1 by L integral x dx. Now limit will not go from 0 to L. You see, limit will now go from, for example, say if this is 0, this will be L by 2 and this will be minus L by 2. Okay, since we are taking the coordinate system from 0, the positive coordinate here positive x and here negative x. This is L by 2. So for the whole rod, the limit will go from minus L over 2 to L over 2. Alright. This is obvious. Minus L over 2 to L over 2. And now we can calculate. Alright. Or another thing we can do, we can take it individually. R equal to 1 over L. We can divide this limit as integral minus L by 2 to 0 and then integral 0 to L by 2. Nothing will change, everything will remain same. Alright. We can club these two as this. So for positive half, I have taken 0 to L by 2. For negative half, I will take minus L by 2 to 0. We can club this and we will get this, and obviously x square by 2 minus L by 2 and L by 2 minus won't have any effect. Both will cancel out and this will be 0. So you see, center of mass is at 0 distance from this axis. This means on the rod, this is 0 distance. This means the point at which this axis is passing. Alright, that is only the center of mass. So here center of mass is O. Alright. Now let us give another twist to this question. For example, these are 2 points. I want to find out the center of mass from this axis, which is at a distance of L by 4 from the center. Alright. Now how do I find the center of mass? Obviously we go by standard method. We take this element mass dm of length dx at a distance x. Alright. So what will be the center of mass? R equal to integral x dm by integral dm, right? And this will be equal to integral x, this will be m over L dx by m. This cancels out. R would be equal to 1 over L integral x dx. What will be the limits now? Limits will be from, since this is L by 4, minus L over 4. This is gone into negative because this axis we are assuming origin, to L over 4 plus L over 2. This will be equal to 3L over 4. So this is L over 4 minus, and this whole is 3L over 4. So this will be equal to minus L by 4 to 3L by 4. What is this? This will be equal to, since x dx is half, 1 by 2L x square, right? This will be minus L over 4 to 3L over 4, right? So LL we take out, so this will be L by 2 times 3 3s are 9, 4 4s are 16, minus 1 by 16. This would be 8 by 16, or we can say half. L by 2 times half, which will be equal to L by 4. Alright, so center of mass is at L by 4 from this axis, and this is positive, so we have to take this, and hence we arrive at a point O. So what I want to emphasize by taking this, twisting this question is that from wherever you take any axis, always this point will arrive, always O will arrive, always. Alright. So I want to emphasize that any axis you take, always O, always center will arise if the body is symmetrical. Alright. Now suppose I take a hollow square. Okay, this part is hollow, and this is a square ABCD. Now I want to find out the center of mass of square. So how do I do it? You see, hollow square can be thought of as made up of 4 different rods. 4 different rods are AB, BC, CD and DA. Since the middle portion is, since this portion, black portion is hollow, this means these are individual rods. We can consider these as individual rods. So already I have told you individual rods have their center of masses at center. Alright. Suppose this is L. Center of mass will lie here, equal L by 2, L by 2, here also, and here also. Alright. So the line which connects these all 4, and the line, these 2 lines joining the center of masses meets at this point. So this is the center of mass. Alright. So if this were to be solid, and if I were to apply a force over here, the square was to be balanced then. Alright. This is a very simple approach. We can apply, we can do it very simple. Suppose now we have a solid square. Since square is solid, so we cannot assume this as a square as made up of individual rods. Now I want to find out the center of mass from this axis. Say axis passing through one end. This is Y. Now, what do we do? First of all, we take a strip of mass. Let us say this is a strip of mass. Okay. Now, you see area of square is L square, and area of square will remain L square. Alright. Area is constant. So we can take mass per unit area as constant. Since mass is constant, so we take this value mass per unit area as constant. So what will be the mass of this? Mass of this piece will, which is of width dx. Say dx at a distance x, and this, say length of mass is dx and width is L. Alright. So this would be equal to m divided by a times the area of strip. So this will be the elemental mass of strip. Alright. And area is L square over here. So dm would be equal to m divided by L into dx. And what will be the center of mass? R would be equal to integration x dm divided by integration dm will be m. So R would be equal to integration x times m divided by L dx by m. Gets cancelled out, 1 over L integration x dx. And what will be this? This will be from 0 to L, because axis is along the edge. So we consider the edge as origin, and the final length will be L. So 0 to L, this will be equal to L over 2. We only have a rough idea that center of mass lies somewhere along this axis, which is at a distance L over 2. Alright. But do we know the exact point? We don't know. Because from this axis, anywhere center of mass can lie. To know the exact point, we have to calculate the center of mass passing through axis AB. Alright. Passing through the edge AB. This will again appear to be at this at a distance L by 2. Now we have the correct point. This is the point where center of mass lies, which is at O. Alright. So this is for a 2D figure. Okay. So you see, we saw in the earlier example that center of mass needed 2 coordinates for a square plate. Okay. For a 2D dimension, we need 2 coordinates. Alright. So they were L by 2 comma L by 2 where the center of mass lie. Okay, now for example we take a circle. Okay, so we take two axes, this is X and this is Y, and this is a circular wire. Now I want to find out the position of center of mass of this wire. Let us consider this position as O, and O is the origin over here. Okay, let us take an element of mass M as we did. This element has a width, okay, ds, and this angle is theta and this angle is d theta, and this is the radius of the circular wire. So what is ds? ds would be equal to r d theta. Alright, and what will be dm? As I earlier told you, dm is lambda into ds. Alright, lambda is mass per unit length. As this is a wire, its length will be constant. L will be equal to 2 pi r. Alright, so we can take lambda as m divided by 2 pi r times ds. This is dm, and ds was r d theta, so m divided by 2 pi r times r d theta. This is equal to dm. R gets cancelled out. dm equal to m divided by 2 pi times d theta, right? So this mass element has two coordinates actually. You see, it does not have one coordinate as was the case with rod. You know, in also square plate there were two coordinates. One was from this axis and one was from this axis. And this is similar because, you know, from this axis we can take this coordinate as down and this point was reached. So here there are two coordinates formed. If we take projections, this x coordinate of the mass is r cos theta and this y coordinate is r sin theta. So it has two coordinates. Alright. Since the element mass has two coordinates, we will have to find out the position of center of mass by integrating using these two coordinates. Alright. Since dm was m by 2 pi times d theta and x coordinate is r cos theta and y coordinate is r sin theta, right? So what is center of mass? What will be xcom? xcom will be equal to 1 by integration dm integration x times dm, right? This is m. What is x? X is r cos theta. And what is dm? dm is m over 2 pi times d theta, right? This gets cancelled. So what is the limit? Since it is the whole circular wire, this will go from 0 to 2 pi. Alright. So we have xcom to be integration r divided by 2 pi cos of theta d theta. It will go from 0 to 2 pi, and cos theta d theta is the integration is, since the differential of sine is positive, hence the integral of cos shall be positive sine. So we have sine theta and it goes from 0 to 2 pi. Sine 2 pi 0, sine 0 0, so this is 0. So xcom is 0. Alright. This comes out to be 0. Now what is ycom? ycom will be equal to 1 divided by integral dm integration of y dm, right? And y was r sin theta, dm is m divided by 2 pi times d theta, and integration of dm is m gets cancelled, and ycom becomes, and this goes from 0 to 2 pi. Alright, since it is a full length circle, this becomes r divided by 2 pi integral sin theta d theta 0 to 2 pi. Since differential of cos is negative, hence integral of sine shall be negative. So this will be negative cos theta. We can take negative outside. Cos 2 pi is 1, cos 0 is 1, 1 minus 1 is 0. So hence this is 0. This is minus r by 2 pi times cos theta, and this is 0. So we found out that the center of mass for a circular wire was at its origin. Alright. 0, 0. This is what I am trying to tell you. Alright. Since there are two coordinates, center of mass comes out to be 0, 0. Now I just twist a problem. I am twisting the same problem. I am taking a semicircular wire. Now what happens? You see, semicircular means only half a circle. Alright. Now I want to find out the center of mass, the position of center of mass of this half circle. Doing similarly, you take this axis as x, this axis as y, and this elemental mass as dm, right? dm forms an angle d theta with the x-axis. dm has a width, forms an angle theta with the x-axis, and dm has a width d theta of it. dm has a length of ds, and in standard notations we can write ds equal to r d theta, where r is the radius of the semicircle. And now we see the coordinates of dm. Again, these are r cos theta and this would be r sin theta. These are the two coordinates of dm. So what will be dm now? Since length is constant, we have m divided by l. What is l? L is not 2 pi r here. Because it is a semicircle, it will be pi r. m divided by pi r times ds. And ds is r d theta, right? So r gets cancelled out. dm is m divided by pi into d theta. So dm is m divided by pi into d theta. Now the x coordinate of dm was r cos theta, y was r sin theta. So we'll calculate the center of mass using these two coordinates. So we have x com as 1 divided by integral of dm integration of x dm. This will be equal to r cos theta times m divided by pi into d theta divided by m. mm gets cancelled out. This is x com. X com would be equal to integration of 0 to pi. You see, this will go from 0 to pi as this is a half circle. As this angle is assumed to be 0 from here till here, anti-clockwise 180 degrees. That's it. So this would be equal to r divided by pi cos theta d theta. You see, cos theta d theta comes out to be sin theta, and the limit put over sin theta. Sin pi is 0, sin 0 is 0, so we get 0. So x com is 0. So now we know that the x coordinate of center of mass lies at origin. Alright. But it is not this point. Okay. It lies along this line because y axis is essentially x equal to 0. This axis of y is essentially x equal to 0. So x can lie anywhere over this axis. Alright. For that, for finding out where it lies on y axis, we will have to calculate the y coordinate of center of mass. So y coordinate of center of mass will be y com would be equal to 1 divided by integration of dm integration of y dm. Y com would be equal to 1 divided by m. This would be equal to r sin theta, and this would be equal to m divided by pi times d theta. And obviously, as before, this will go from 0 to pi, and mm gets cancelled out. Y com is r divided by pi integration of 0 to pi sin theta d theta. And obviously, sin theta d theta is minus cos theta integration, because differential of cos is minus sin. So we get y com equal to r divided by pi minus cos theta, and this goes from 0 to pi. Cos pi is minus 1. Minus of cos 0 is 1, so minus minus gets minus 2, and minus is outside, so plus 2r by pi. So this is y com. Hence the net center of mass will lie where? For a semicircular ring, actually, yeah, this is the semicircular ring. Center of mass will lie somewhere here, 0, 2r divided by pi. This is 0, 0. Alright. This is the center of mass. So if we pass a rod over here and try to balance it by applying force at this point, the whole wire will be balanced. Alright. So guys, this was my analysis of center of mass. I will post the next video on motion of center of mass, moment of inertia, and then we will move on to rotation. Okay. And from that we can move on to gravitation and fluid mechanics. Okay. Please like, view, review, subscribe and recommend. Okay. And please do watch this. This is a video of basic concepts, so please watch it many times as you can. This will clear your basics out. Okay, thank you very much.